Welcome, everyone. I am absolutely thrilled to have you here for today's explainer. We are going to embark on a truly fascinating journey today. We're zooming all the way in to look at the invisible forces of the quantum realm, and then we're going to slowly scale all the way up. We'll go through chemistry and biology right up to our massive planetary ecosystems. And finally, we'll cap the whole shebang off by looking at the art of how we actually teach these incredible concepts to the next generation. It's a massive scale, but I promise you the connections are going to blow your mind. Let's get into it.
Okay, let's dive right into this roadmap. First, we'll hit forces, energy, and atoms, then see how those combine in the chemistry of matter. After that, we scale up to biology, zoom out to Earth and its environment, and finally wrap things up with the art of teaching. Section 1. Forces, Energy, and Atoms. The building blocks of the universe. This is where the fundamental rules of reality are written, so we really have to start at the absolute smallest scale.
Now, you might be wondering, what actual force holds atoms together? I mean, we know gravity grounds us to the Earth, right? But what keeps microscopic matter from just flying apart? Well, the answer is the strong nuclear force. It's literally the incredibly powerful glue holding atoms and molecules together to form larger bodies. Honestly, without it, the macroscopic world, and yeah, that includes you and me, simply wouldn't exist. And this brilliantly illustrates how tiny subatomic shifts can basically rewrite reality. Protons, they dictate the actual identity, the atomic number of an element. If you gain or lose an electron, you radically change its electrical behavior and create an ion. Tweak the neutrons, and boom, you've spawned a brand new isotope. These three little particles completely dictate an atom's chemical destiny. Now, when these physical bodies interact in the real world, energy gets transferred. Think of it like this. In an elastic collision, objects bounce off each other and remain separate. But in an inelastic collision, they crash and fuse together into one single moving unit. It's a perfect everyday representation of how momentum and energy govern our physical world.
Okay, let's challenge your intuition a bit before we scale up to chemistry. In which medium does sound travel the absolute fastest? Is it wood, water, or air? Think about how densely packed the atoms are. If you guessed wood, you are absolutely right. Sound speeds through tightly packed solids. Let's move to Section 2, the chemistry of matter, and see how these atoms actually combine and react.
So, chemistry is really all about how things mix. When measuring solutions, there's a vital distinction you have to make. Molarity relies on the volume of a solution, meaning it is totally dependent on temperature, because, liquids expand when they heat up. Molality and mole fractions, on the other hand, rely on mass or moles, so they don't care about temperature swings at all. And these chemical concentrations actually dictate cellular life through a process called osmosis. Drop a living cell into a hypertonic solution where there's more solute outside, and it aggressively dehydrates and shrinks. But put it in a hypotonic environment, and water violently rushes in until the cell swells and bursts. It is a really delicate life-or-death chemical balance. The cool thing is, we harness these exact same principles in our own kitchens every single day. That cooling effect in your fridge, that is just the physical chemistry of vaporization absorbing heat. And popping open a soda, you're immediately dropping the internal pressure. That reduces the gas solubility, forcing the dissolved carbon dioxide to rapidly escape as bubbles. And since chemistry completely dictates cellular behavior, that brings us right to Section 3, biology, cells to ecosystems, the web of life. Because when you get down to it, biological life is really just incredibly complex chemistry. I love how perfectly this illustrates the biological hierarchy. It scales up so beautifully. Individual cells autonomously group into tissues. Tissues architect the organs. Organs synchronize into complex systems, and suddenly, boom, you have a complete living organism. It fits our micro to macro journey perfectly. Now, what's really interesting about this is the architectural process of animal development. It's just breathtaking. From a single zygote, rapid active cleavage forms a hollow fluid-filled blastula. Then, cells actually migrate during the gastrula phase to establish 3 primary germ layers. Finally, in the neural phase, the ectoderm elongates to form the neural tube. It is literally a miraculous microscopic choreography.
But of course, organisms don't just exist in a vacuum, right? They operate within highly complex food webs. It's a massive, cyclical flow where energy, initially captured from the sun by producers, relentlessly cycles through a vast, interdependent network of consumers. Now, to house all these massive biological webs, we need a planetary stage. That brings us to Section 4, Earth and its environment, our planetary home. Surrounding our Earth's surface is our incredibly vital atmospheric shield, and while it stretches all the way out through the stratosphere, mesosphere, and thermosphere, right up to the exosphere, it's important to note that nearly all of the weather and climate events that actually shape our daily lives happen right here in the lowest layer, the troposphere. And Earth's history spans an absolutely massive geologic scale. We're talking from the oldest Precambrian era, through the Paleozoic, into the Mesozoic with the dinosaurs, all the way to our current mammalian Cenozoic era. Over these massive stretches of time, our planet's temperature and environments have been in a state of constant, dramatic fluctuation. Even today, dynamic cause and effect relationships continue to rewrite our environment. For instance, global warming involves the greenhouse effect trapping infrared radiation in our atmosphere. Meanwhile, cyclical events like El Niño can completely alter weather patterns, causing a lack of rain that leads to widespread droughts and crop failures.
But hey, mapping out the universe and our planet is really only half the battle. The other half is figuring out how to share it. Let's move to Section 5, the art of teaching, passing on the knowledge.
So the crucial point here is that teaching science isn't just about reciting facts. It's about matching the pedagogy to the student's unique learning style. Take the project method, for example, which requires students to present concrete forms of how principles work. Having students physically build models of atoms directly targets the kinesthetically intelligent learner, the kind of person who really needs to touch and build things to truly understand them.
This whole idea of different learning styles brings us to a really beautiful quote from psychologist Howard Gardner. He said, "The individual who is readily able to recognize flora and fauna and to use this ability productively is exercising an important intelligence, deeply rooted in a sensitive, ethical, and holistic understanding of the world." I absolutely love this. It ties our entire scientific journey right back to human observation and our deep inherent connection with nature. So, I'm going to leave you with this final thought. A math teacher once wisely noted that to every question there is an answer, and to every problem, a solution. In a universe as beautifully interconnected as ours, from invisible atoms all the way up to our vast atmospheres, what undiscovered solution will you find when you start looking for the right answers? Thank you so much for joining today's Explainer, and as always, stay curious.